Hello everyone, in the previous video we introduced the concept of ensemble. In particular, an ensemble is a collection of microscopic state for a system under a given thermodynamic condition, right? Now for a system under constant number of particles, volume, and energy, the corresponding microscopic state, collection of that state is called a microcanonical ensemble. And we know that if we map all of the possible microscopic state into the phase space, right, such microscopic state is going to sit on the surface because total energy is conserved, right? And then also very important concept we introduced about ensemble is that we can take the so-called ensemble average, which means that you can just average over the states, right? Instead of doing the time average, such that you can compute the average properties of the system. So this particular state average is what we call the ensemble average. And now the very important quantity is P here, which is the probability of finding a particular state V in the system. For a microcanonical ensemble, this probability is a little bit trivial, which means that all of the states have equal probability of being found. And then if the total number of states is omega, and then we know that the probability of finding each state is just 1 over omega. So you can plug this back in here, and you know that the average properties simply can be computed by randomly sampling the states, right? And then you sample all the states, sum it over, and then divide it by the total number of states. That's going to give you the average properties. Now, how about a different system? How about a system under different conditions? Another commonly used system in many materials study is a system with fixed number of particles, volume, and temperature. So instead of fixing the energy by isolating the system from the rest of the universe, we just place these particles in a box, and then we consider the box has a thermoconducting wall, which means that there can be heat exchange between the system and the environment, right? So, and then the temperature of the system is simply set by making the system in equilibrium with the environment. So the temperature of the environment basically going to be equal to the temperature of the system. So in this way, we set the system as an NVT system. And as you can see from this particular setting, although the system have a fixed temperature, but the energy of the system is fluctuating, right? Because at any time point, the system can lose a little bit of heat or it can receive a little bit of heat. So the internal energy of the system is fluctuating. Nonetheless, we can still do the same thing as we did for the NVE system. Namely, we can suppose that ideally we can enumerate all of the microscopic states, which is given by the set of all the positions and the velocities at any snapshot in the system, and we can map this microscopic states to the phase space. Now, the phase space is much more complicated compared to the microcanonical ensemble, right? So, for example, you don't have a very simple trajectory, closed trajectory for the states, but the states are actually distributed. You have a certain distribution of the state in the phase space. Okay. Now we call this particular collection of the microscopic state for NVT system, we call this a canonical ensemble. Again, it's a collection of all of the microscopic state for the NVT system. This defines a canonical ensemble. Now, following very similar idea of microcanonical ensemble, if we're interested in calculating, for example, the average energy of the system, we can do an ensemble average, right? So the way we do that is that we can simply, sample all of the possible states, and then we know what is the energy for this particular state. But now the most important thing is that how can we find out the probability of finding a particular state labeled with energy EV? We know that for microcanonical ensemble, each of the states have exactly the same energy, so the probability of finding each of the state is exactly the same. But for now, because each state have a different energy, so the probability should also be different. How do we find out this probability? Okay, to get the probability of finding a particular state in the canonical ensemble, we consider this particular setup. Namely, we consider you have a very, very large box, maybe as large as the entire universe, right? Of course, it's a parallel universe. And then this box is isolated from, everything else, right? So this is very large box and then it's isolated from everything else. That is our setting. And then we consider that within this super large, infinite large box, there's a small portion, Okay, I have a smaller box. And this box is where what we're interested in. So this box has a fixed number of particles and then fixed volume and a fixed temperature. So this smaller box is actually is part of the subsystem for this very large box isolated from the universe. But this box is giving us our canonical ensemble. Okay, so that's the setting. Okay, so now we consider that very large box, right? In the super large box, the total number of particles is given by this n, and then the volume is given by this v, and then the total energy is given by this E, right? So this one gonna defines a NVE system, right? Now remember that the total number of particles in this very large isolated box is much larger than what we have in our system of interest, right? So in this particular setting, suppose that at some time point we find the system is in a particular state V with energy EV, right? My sub-box is in this particular state. Now we're asking how many different states, right, for the rest of this box can be. Okay, how do we do that? Well, we just consider this total number of states in the rest of my large isolated box can simply be a function of this, right? Because my subsystem takes a little partition of the energy. The energy is fluctuating, right? It takes a little partition of the energy. So the total number of states for the rest of this super large box, right, going to be proportional, going to be a function of this particular energy of the rest of the box. Okay, now we basically claim that in this particular case, right, the probability of finding that subsystem, right, with a particular energy EV is then simply proportional to, okay, the total number of states outside this system in this very large box. Okay, so this is a concept that is not very easy to get, right? Let me illustrate why this is the case. Now, what we do is that now let's focus on this very large isolated box, right? Because this box has a fixed number of particles, fixed volume, and a fixed energy, we know this box, if we map all of the microscopic state for the very large box in the phase space, we're gonna get something like that, right? So this is a microscopic state, the phase space for the very large box, right? So this is xn and this is vn, right? And we know that it's gonna give us something like that, right? So the collection of the microscopic state is gonna sit on a fixed surface, gonna close the surface. So now what we have here is that, okay, now if my particular system is observed with this particular energy, then I'm asking how many different states, right, the rest of the system have that are compatible with this energy EV. So for example, all of these states, right, if we look at the very large box, this is a collection of the states for the very large box. If I look at that, right, each of these states are distinct states for the entire system, but for each of these distinct states, right, if we look at the smaller system, our NVT system, all of these states is labeled with this EV for my smaller system. Okay, now you count, okay, what is the total number of that? Oh, that total number of these states is gonna give you this omega. Okay, so that is the basic idea, right? So the probability of finding that particular substate with this energy EV is proportional to the total number of states for the rest of the system that's compatible with this energy, right? Now, why this is the case? Well, it comes from this microcanonical ensemble idea, right? Because for this NVE system, this large NVE system, every single state have the same probability of being observed, right? So the total number of that state compatible with this EV for your subsystem basically give you the probability, right? It's proportional to that probability. So now suppose that, let me further illustrate this. If you have a different state, right? I call this PS, right? And then it's labeled with energy S. Now this is going to be proportional to this thing, right? So take this energy away. So I'm using the blue for that. Well, maybe there's only a smaller number of that, only probably 3 of those states, right? So you see that the probability of finding state V then is larger than the probability of finding state S. So that's basically where it comes from. Okay, now let's take this insight. Okay, let's take this one and see if we can do something to simplify this to get some even more interesting results. Okay, so let's take this insight and see if we can do some statistical manipulation to make this easy to work with. Okay, so first thing is that, okay, we start with this, right? But we don't want to directly work with the number of states. That's a very large number, right? So let's find a way to simplify this a little bit. So the trick is by construction, right? We'll do this. So we introduce a exponential function, and then we, instead of working with omega, so we work with log omega, right? So let's do this. Okay. And also, once we're here, we know that this E, the total energy of my large system, is much, much larger than whatever the fluctuating energy for my subsystem, right? So basically what we know is that this energy is much, much larger than this particular energy. So now what we could do is that we can expand this log function, right? Log omega function, in terms of the small perturbation in certain sense of EV, right? So now let's do that. We know that if we want to do, a Taylor expansion for this guy, right? So this basically equals to the function at this energy E, right? Plus the first order derivative of this function, which is partial log omega, partial E, right? And then this is very small perturbation, which is minus EV plus higher order terms. Now, because we consider EV is much smaller compared to the overall energy, we ignore the higher order terms, right? So now one thing you realize that if we plug this expansion, this whole term, back into this exponential, we don't have to worry about this term anymore, right? Because here, this is proportional, and we know log omega for fixed energy for the very large system is a constant, right? So we're not really interested in this constant. So now the insight we get is that using this trick for writing this as exponential and then do a Taylor expansion, right? We get insight that this PV, okay, for finding a particular state labeled with energy EV, now is basically given by the exponential function, and then you have minus log, partial log omega, partial E, and then times EV. Okay, so now we're here. Okay, so now let's do some further mathematical tricks, right? So this will use some additional thermodynamic knowledge. We will talk about this in a different video, but here let's just assume this is the case, right? So we know Boltzmann introduced a very useful expression for the quantity called entropy, right? And according to Boltzmann, right, entropy is simply given by, which is denoted by S, K log omega. Well, this omega is the same omega that we're dealing with. It's the total number of states for a NVE system, right? And also we know from thermodynamics, when we combine the first law with the second law, that the partial derivative of the entropy with respect to the energy is simply equals to 1 over T, right? So now you combine these two together, what do you get? If you combine these two together, you have partial S, partial E, which plug in the expression is partial K log omega, partial E equals 1 over T, which means that partial log omega, partial E equals to 1 over KT. Okay, so this is a very interesting and important result for our derivation. So again, it comes from some fundamental knowledge of thermodynamics, which we'll introduce in a different video. But for now, let's just take this result, and then we're going to plug this result back in here and see what we get, right? So now we know what is partial log omega partial E, which is 1 over KT. So once we plug this in, what we get is that the probability of finding a particular state labeled by EV is simply proportional to the exponential minus EV over KT. Okay, that's a very interesting and a very insightful result, because we know that the KT set a particular energy scale for a given temperature, right? K is what we call the Boltzmann constant. The unit is joule per K, where Kelvin, and temperature is given in terms of Kelvin, so K times T equals to the energy, right? So this is energy scale set by the thermal fluctuation, and then this EV is, of course, the energy of a particular state. So this is very interesting, right? So it tells you that the probability of finding a particular state with energy EV is proportional to the exponential of minus of that energy. And of course, this is set also by the thermal fluctuation. Okay, so that is a very interesting insight. And in statistical mechanics, typically we introduce a quantity called beta, which is 1 over kT. Sometimes we call this the inverse temperature, right? And using this expression, you'll see that the probability of finding a particular state can be written as E minus beta EV. Okay, so this is basically the probability of finding a particular state in the canonical ensemble, right? Now, just a quick recap, right? This is what we have. And then the system, what we have in mind is, you have a bunch of particles in the box, and these particles move around, right? And you can take snapshots of this particular system to define the microscopic state. But now this box has a thermoconducting wall. So if we consider thermal equilibrium, the box is set by a fixed number of particles, fixed volume, and a fixed temperature. And if we're interested in a particular state, right, with energy EV, the probability of finding that state is simply given by this. Okay, now if you look at this carefully, right, we claim this is a probability of finding the state, but you see that this is not a definitive relation because this is just a proportion, right? This is not equal sign. How can we convert this to the equal sign? Well, we know one thing about the probability is that if you sum over all of the probability, right, and then sum over all of the states, right, this has to equal to 1. Okay, so now let's say, okay, let's assume based on this particular insight we have, the probability of finding state EV equals to, this is the key factor, and then we have a common denominator, right? And we call this factor the Boltzmann factor. Okay, which is known if we know the value for that particular EV, right? So this one is what we call the partition function. We don't know what this is, right? But it's easy for us to get that because then we can easily plug in this PV in here. So this means that we take sum over all the states, and then this is basically the states, and then this is Q, this equals to 1. Now we know that this partition function has nothing to do with individual states, right? So it does not have anything to do with the sum over the states. So we can take it out, and then you simply have sum over all of the Boltzmann factor for the states divided by Q equals to 1, which means Q, which is your partition function, equals to sum over all of the Boltzmann factor. Okay. Again, a very, very interesting results. Okay, so now we basically have the partition function, which is the denominator, and we can plug this back in here. And in principle, you get all of the microscopic states, right? You get the probability for all of the microscopic states. Okay, so now let's write down that explicitly. If we take all these insights together, now what we get is the probability of finding the microscopic state labeled by EV for this canonical ensemble is simply given by this, right? The Boltzmann factor and associated with energy EV divided by the partition function Q, and the partition function Q is given simply by the sum over the Boltzmann factor for all of the states. Okay, so that is the probability for finding a particular state in the system for a canonical ensemble. Okay, this is what we're looking for. Okay, now let's demonstrate how we can use this to get some additional insights. Okay, so one of the things, as we mentioned, why we want to use this probability, why we introduce this, is because we can compute an average quantity, right? Suppose we're interested in computing the average energy E of the system, right? We know that this energy E average energy E can be basically computed as this, right? You do a state average, which is also the ensemble average, right? So basically sum over all the states, and we know that particular state has this energy EV, and the probability of finding that state is given by PV, and then we just weighted sum is basically going to give you the average energy of the system, okay? So now, because we already know the expression for this PV, right? So we can simply plug this in here, and let's write down this calculation explicitly and see what we get for the energy E, the average energy E for the system. Okay, so now let's just work on this. So the average energy E simply equals to the sum over all the states and the probability. So let's plug in the probability, which is minus beta EV, and then you have EV. Okay, that's basically what we have. So let me just have this 1 over Q here. So you have the sum over the state minus beta EV and EV. Okay, so the interesting thing is that if you look at this particular term, and you immediately realize that, okay, so if I work with this Boltzmann factor, and then if I take the derivative of this factor, which is an exponential function, with minus beta, and I directly get EV out, right? Basically, this means that if I do this, d minus beta, I get an EV out, okay? So this means that, okay, I can replace this EV, okay, I have this EV and also times E minus beta EV, right? So I have this term, I have this whole term here, and I can write this in terms of a derivative. Okay, so how about we do that? Let's do that. Okay, so let's continue to simplify this, right? Instead of keeping these like that, let's just write down this as a derivative. So this is basically the derivative of E minus beta EV with respect to minus beta, right? Now, because the sum is interchangeable with differentiation, so what we do now is we do this, and then this is d minus beta, and then we have the sum over the states, the Boltzmann factor. Okay, now you can immediately recognize that this whole term now give you Q, right? So basically what we have for now is the average energy equals 1 over Q, and then this is dQ d minus beta. But we also know that dQ 1 over Q, this is d log Q, d minus beta. Okay, so that's a very interesting insight, right? So this means that the logarithm of the partition function seems to contain a lot of information about the thermodynamics, right? Because the average energy of the system, or the energy of the system, can be obtained by taking the derivative of log Q with respect to minus beta. Okay, this is a very important and very interesting result, right? This means that if you're interested in getting the average energy of the system, well, you can definitely go ahead and sum over the states as we did before. But we show that if you do that, this is going to give you something that has this closed form, right? It's equivalent to just to take the logarithm of your partition function. Again, the partition function Q is the sum over the Boltzmann factor for all of the states, right? So you take the Boltzmann you take the logarithm of the partition function, and then you take the derivative of that with respect to minus beta, and you get E, which is the average energy of the system. This is a very, very interesting result. Now we can think more about this, right? So now we know beta is the inverse temperature. So it's not quite obvious to work with beta. Let's try to see how I can convert this d beta to dt, right? Because we know that in thermodynamics we work with temperature a lot. See, what is the relation between these two? Now we know beta equals to 1 over kT, right? So now d beta, so if we consider that, basically d beta is 1 over k d 1 over t, right? And then we know that if we take this 1 over t as a function, we have 1 over k, and then this is minus 1 over t squared dt. Okay, so this means that, okay, d beta simply equals to minus 1 over kt squared dt. Okay, again, a very interesting results. Okay, so now the interesting thing is the following, right? So we have the energy E, and then this d log Q d minus beta simply equals to d log Q, okay? And then we have 1 over kT squared dt. Okay, so now basically what I'm going to do is to write down this as k times t, and then I have log Q, and then I have this dt, and then this is squared. Okay, so this is basically what we have, right? So this means that, okay, I have the energy of the system, and the energy of the system seems to equals to some function, right? And then we take this derivative of this function with respect to the temperature. Okay, so that's a very interesting relation, right? Because we know that you can only get the energy E from a thermodynamic function, right? And in fact, right, if we compare this relation to existing thermodynamic relation, we can identify that this quantity minus kT log Q gives you the Helmholtz free energy of the system. Okay. So for this particular video, we're okay with this result, and we're going to show how this is exactly connected to the Helmholtz free energy in a separate video.